Okay. Hello, everyone. I think it's been almost like 2 weeks since the last time I streamed, but nonetheless, I think last week I published a video. Let me check. Yeah, I published a video about Axolotl and the challenges that I had for installing it on HPC systems, and I explained it in details in that video. So instead of streaming, I worked on this video, and since the number of hours I want to put into YouTube is limited, I did not stream. But now, I think this week, I'm gonna again write a bit of blog post regarding another topic that I encountered, and I think for me it was a important topic, and I'm gonna write about it, and hopefully it will also help someone along the way somehow, and probably later on also will create another YouTube video from it. But nonetheless, there was also a discussion last time during the stream. There was a discussion that I have to continue with this SaaS building project, and I have to continue working on that, or that was more interesting than writing blog posts, of course. But I think at this moment I feel like my intentions are mainly in creating some content that kind of reflects my work, so it would be more reliable as a portfolio. So I will probably get back to the SaaS building and developing the website, but at the moment I'm more in the mood of the portfolio writing, or like portfolio development, and also I feel like it kind of matches more to my goals, I would say. But nonetheless, there was also another discussion basically in the same direction, that here the website is not maybe as functional, or like, how should I say it, as viable as possible. So I mainly we're probably gonna kind of remodel, or like find maybe another approach to the current service. So we have to kind of probably reformat and reevaluate the whole approach, and whether this is a viable product or not. There's also another couple of ideas here and there, but at the moment I'm kind of I don't want to say I'm done with SaaS building, but at the moment I'm going to put a pause on it, or until I again find the motivation to continue with it, or like I would be a bit more sure that this is the direction that I want to work. But to be honest, I also don't want to kind of give up. I don't think this would be considered giving up. But at the moment, this is the state that I have in mind. I know maybe it's not really fair, or like really logical to do it, because usually these things pay off in the long term. But one main concern that I had regarding building this service was that my optimal goal was not to generate AI slop, so I don't want to further contribute to AI slop. And for me, it's kind of hard or like really time consuming to like curate the prompts or like curate the workflows. And I think in the end it's probably gonna be AI slop anyway, at least at this stage of the LLM models. Of course, there are really good text out there that are also generated by AI, but the problem is that if I want to go down this road, I'm sure I'm gonna spend, I don't know, many hours on just prompt engineering and then trying to kind of figure out what works, what does not work. And to be honest, my expertise or like my experience with prompt engineering is that it's a little bit how should I say, there's no novelty, I would say. And since there's no novelty, it gets boring pretty fast. I have to constantly try something and then see what's wrong or like how it can be improved, and then try to change the prompts again. And usually it's that one change, the newest change would ruin something good from the previous changes or like previous prompts. So it's like this back and forth until you find the optimum, or like to some extent optimum prompt for the workflow. And when I look at it, I, to be honest, don't want to spend my time like this, because as I said, prompt engineering, at least for me, from my point of view, there's no novelty to it. Of course, almost, I mean, these days most of the developments are mainly just prompt engineering and trying to just extract the last ounce of maybe creativity of the LLM models or language models. But at the moment, I'm not really, I don't want to invest that much time into just working around, like playing around with the prompts. So that's one of the reasons that I'm not really confident or like really motivated for continuing this service, because it's gonna involve a lot of prompt engineering, and to be honest, I'm not sure if it's worth it or not. And also, in the eyes of the public, AI content is a little bit shady at the moment. I mean, everyone kind of understands AI is slop, or like when they read it, they realize that it's kind of like just random stuff put together nicely, and then kind of doesn't have any human aspect to it. And in general, there's a negative aspect, or like negative point of view towards the generated text, which I totally understand. And I also am really personally also a bit skeptical about the generated output. And sometimes, for example, when I'm reading a blog post and I see that it's generated by AI, I feel not that good. And I feel like if I wanted to follow on this idea, there's a chance that I have to kind of overcome the public opinion regarding the generated text, which is kind of, to be honest, won't happen overnight. So I think the best option is to reevaluate and try to come up maybe with the next service, and try to go from there, or like find some direct customer, like from the close circle of mine, for example, friends, families, and this sort of potential customers, and maybe create a application profile, like customized them, and then we might be able to take it from there. But at the moment, the idea that I won't continue with this, or like at the moment I put a pause on it, is mainly, first of all, I feel like the development process would contain so much prompt engineering. And to be honest, prompt engineering, for me at least, there's no novelty. It's super boring, and I don't feel I get any value out of it. And on the other side, like the second point is that also the public view of this approach is not really ideal, or like there's people are skeptical regarding AI generated output, and in general AI is slop, and these are the things that would be the main challenges for me. So at the moment I'm putting a pause on it, but later on we'll see if you want to continue maybe with another platform, like another like SaaS idea. But that said, I want to continue with writing another blog post, and I think we can create another folder like the last time, and then we call this one maybe Parallelism for LLM Inference, like types of parallelism for LLM Inference. And again, there would be this index.md file. Okay, just to keep the format again. This would be like for the first. Types of parallelism, LLM Inference explained. Deep learning explained. Yeah, in general, I think it's almost the same idea. I mean, whether it's a transformers architecture or it's like a deep neural network, I think the types of parallelism are gonna be the same concept. Like the idea is the same. Of course, I have some charts though that I want to kind of share along the way, but yeah, so the main idea, if I want to explain it, is that I had this experience, like experiment with I wanted to like serve some LLM model. I think the LLaMA 8 billion or so, LLaMA 3 8 billion, and the idea was that I had 4 GPUs available, and the idea was to just maximize the utilization of these GPUs, of course, to just use every ounce of computing power that I can get, and along the way I would just generate maybe, I think, around 4,000 data set, like synthetic data. And the main problem was, so basically I had 4,000 prompts, and then these prompts should have been processed by the LLM. So that's the whole idea. And then this shows the utilization of the accelerators, or like the GPUs. And as you can see, the utilization is really weird and really bad. And usually you want to all the utilization to be above 80%. So even, I mean, the ideal case is that it's really close to 100 or like even 100, but of course it's really hard, or like maybe in an application it's almost impossible. So we're aiming for like the region between 80 or like 100. But this workflow, as you can see here, it's really bad, and it's not fully utilizing the GPUs. So the idea is that I mean, the problem that I had was that I couldn't really fully utilize the GPU, and then I just changed the type of parallelism. For example, this one, if I'm not mistaken, this was this was like pipeline parallelism. And let me show the other graph. And then I just changed the parallelism type from pipeline to tensor, pipeline parallelism to tensor parallelism. And then as you can see, like the GPU utilization just stayed on top above 80%, which is like almost perfect. So this means that the GPUs that I have are fully utilized and fully I'm getting the performance out of the GPU, so it's like I'm not wasting anything. That's an important factor. Of course, there's also another thing that I learned along the way, is that there is a chance that your utilization is high, but your power consumption, which kind of indicates the amount of computation that you are doing, is not fully maxed. For example, if a GPU has a power capacity of 300 watts, if your maybe there would be a scenario where you are fully utilizing the GPU, but then the power is kind of fluctuating around maybe 200. So it's like there's 100 watts gap that is not being used, which is okay, because this shows that your workflow, or like your scenario in this case, is not really compute bound, which is like you are of course doing some computation on your GPU, but it's not really fully using all of the computation capabilities of your GPU. So this difference between use like this wattage is from this, and it kind of correlates to your workflow. But there's a chance that you are also utilizing your so the one that I just explained was that high utilization, medium power usage, which shows that your workflow is not really compute bound, and there's also some memory bound stuff. For example, in LLMs, if you are having a long output, this would be more memory bound. And there's also, there could be another another scenario where you are kind of maximizing your utilization, as you can see here, and you're also maximizing your power usage. So meaning like your workflow is mainly compute bound, which the GPU is forced to use all of the power that it can get. You're kind of pushing the GPU to the very limits of itself. So this is like would be the extreme case, or I mean, it depends on your type of view, but maybe this would be the way to fully utilize a GPU. But in any case, this is one thing that you have to keep in mind. Doesn't necessarily mean that if you have like medium power usage, then you are doing something wrong. I would say it just means that your workflow, like your type of problem that you're solving, is kind of not fully compute bound. So it's also one important factor to have in mind. But the scenario that I had and kind of went with, like happened to me, was that I went from the graph on top to the graph on the bottom only by changing the type of parallelism. So it shows that it's super important to know this factor, this concept, and it also shows that this can be also one way to maybe debug your applications when you want to fully utilize the GPU. So I will keep this somewhere. Maybe I need to explain it later. Let me save it. And GPU utilization. Stream. Okay, so yeah. That being said, we also will put it here. Okay. I also wanted to make this maybe, I mean, I will keep this post as not featured, so I keep my old post here as featured posts, and then when I see that the new post is kind of finished, I will also flag this as featured, or try to unflag the other one as like unfeatured, or I don't know how to say it, but yeah, I will unfeature the other post and make this a newest post, the featured one. Yeah, so that's the idea, and let's get into writing some stuff. I think there are some maybe some big stuff that we can also use, but I think these are irrelevant. Lessons learned. So, okay. So I would say, of course, there's the introduction, and then we can just jump into types of parallelism. Am I writing this correct? I'm not sure. Ah. Parallelism. Parallelism, yeah. Yeah, I hope the dictation is correct. Okay, so there's also, of course, introduction and the types. And then, for example, the first one would be data parallel. And I think the second one, I think data parallel, I would say it's less, I mean, not less important, but I have the feeling that it would be better to put it in the end, because I think there's a chance that I think we probably will come to data parallel less than maybe the other types. So I would put this as 3. Of course, I will talk about it in the end. And then I'll talk about maybe tensor parallelism as the second one. And then the first one would be pipeline. Okay, so 3 different approaches. I also maybe put it here. Okay, so I think here we also should talk about I want to also talk about the I think data bubbles, or like pipeline bubbles, and also here this. Okay, so the TLDR would be the parallelism you choose, aka how to load your, like the way you load your matrices. What's the way you load your matrices on GPUs. The parallelism you choose can make the difference between utilization of, let's say, what's the average of this? I would say it's 50. I mean, it's probably more around 60, but okay, let's just go with 50% and 90%. Okay, so this would be like just the TLDR, like it's important, and this would be like the value, like the way that you do it this can determine the utilization of your GPUs basically. So at the moment I'm going to keep it as the short version, like this TLDR, but later on if I see like something is like there's another value involved, I'll also add it here. Investigate. Yeah, let's just keep it this way. So introduction. This is vLLM, Parallelism. If you I think maybe, for example, let's say if you were ever if you have ever used I think now this is the boring part, I would say, just writing it down. If you have ever used vLLM, you probably came across terms like, okay, single GPU, tensor parallel inference, or pipeline parallel inference, terms in the documentation. Most of the times the reason you decide for one over the other is that is your number of GPUs or amount of available VRAM on each GPU. The number and is number and the amount of available is the number of GPUs and the amount of available VRAM on each GPU. Okay. Each. Okay, I'm not sure if there is also data. Exploit the inheritance, parallels of So visual expert layer. vLLM supports large-scale deployment, combining data parallel attention with expert or tensor parallel MOE layers for information. Okay, I think this data parallel also is interesting. vLLM supports the parallel deployment. Okay, I think it's also better if I share the links maybe. Let me that we had a look into during the stream. Okay, this one, and also I think this one. If you want to, if you're interested to just read a bit yourself, this is also feel free to just click the links, have a look. Okay, where were we? Yeah. Oh, this is also interesting because I didn't know that this existed. Internal load balancing. Oh, wow. Okay, interesting. So basically, so also let me just paint. Okay, so when we talk about I mean, I get to it. Okay, let me just also find the picture. Maybe we have it. So if I find a picture, I can also just use it. Let's put LLM. Yeah, I think this is a good one. Okay, so basically data parallelism is that you copy the entire model. You copy the entire model. Okay, yeah. So basically data parallelism, it means that you copy the entire model on different GPUs. For example, if you have 3 GPUs, then every GPU contains the entire model and kind of like hosts all of the matrices on those on each GPU. So basically you have this replication of 3 models in 3 different GPUs. And then the problem, or like one important factor that would sit next to data parallelism, is the load balancer. So between the requests and the GPUs, there would be this, let me write it here, this load balancer that would decide which GPU has less load on it. So the newest request would be forwarded to that GPU. So this way you kind of make sure that every GPU has enough tasks to be kind of busy with, and you kind of fully utilize out of your GPUs. Because if you have a bad load balancer, there's a chance that one GPU would get all of the work and the other 2 are just like answering some of the requests here and there. So you're basically technically just using one GPU and you're kind of wasting your other GPUs. So a good load balancer is really important. It's also like a really good like a really important component of the data parallelism. Also added here, talk about load balancer and its importance. And then here, I think the DNNs training GPT. Okay, I will also use the images here. I think they're looking good. I will also put it here. At the end, let me also write this tutorial notes. This section will be changed during drafting the post and will be removed in the end. Just want to write down, like, include pictures from this paper here. Okay. Yeah, so as I said, it's really important that you have this load balancer. So now I'm reading that vLLM, it already includes like self-contained this data parallel deployments that kind of exposes only one endpoint. Because technically you can think of it that every of these GPUs, they have, of course, the model kind of enabled on top of them, kind of loaded to them. So every one of them can have this maybe API that you can request your you can send your request to, but when the load balancer comes in, it's only kind of exposes one API. So it gets one API and then requests only to this, and then this will decide, the load balancer will decide which GPU, which model to just send the request to. So whichever GPU that has less load than the others will probably get the newest request. I mean, this would be like really naive or like really high level implementation, or at least that's what I'm guessing that would be a good approach. That if a GPU is kind of idle and other GPUs are just working crazy, there's a really like it's makes sense to just pass the new request to the GPU that is almost kind of free. So that's one thing. And seems like that vLLM also contains this load balancer itself, and it only also expose a single API endpoint. So I think this would be like really easy. So internally, of course, vLLM would load the GPUs, load the model on each GPU and takes care of the loading itself. And also it just will give you one endpoint, so you know that if you request to that one endpoint, and under the hood, vLLM is kind of taking care of everything else. So that's also good to know. Also, it's describing the problem that if you have a lot of data parallelism, then you have all of these different GPUs probably, and then just processing this HTTP server or like this API server, it can also become a bottleneck. So it also goes on and explains like how you can do it to just reduce the bottleneck. Hybrid load balancing. I mean, the amount of engineering detail is really crazy. Okay, so Okay, so if I think we also had it here. If the model is too large for a single node, combine tensor parallelism with pipeline parallelism. Just per node and pipeline parallelism to the number of nodes. Tensor parallel 8, pipeline parallel 2. I mean, we also have to maybe at the end, it would also be really good to talk about this. We'll also add it here. Maybe in the end, we talk about different types. One example to through one example. And here I wanna example explain what happens in such a scenario. How do you write the scenario? Okay. Okay. Okay, so in the end, I also, because this was a interesting example, I would say. I remember when I was reading through it, I wasn't really understanding it, but now I feel like I understand it better. So imagine you have two nodes with 8 GPUs, and then you kind of have to use pipeline parallelism. I mean, the namings are a bit off, but you have to use the third one to just break your tensors, like the whole pipeline, into half, and then you take one half and then you put it on one node and the other half on the other node, and each half would be distributed between No, this is data parallelism. One second. Each half would be distributed among 8 GPUs. I mean, I will explain it more in details when I get to talk about the other type of parallelism as well. But it's like 2 layers of distribution, which is pretty cool, to be honest. So okay, so in general, if I want to give a rule of thumb, I would also want to add on one node just to be a bit safe, because maybe on multiple nodes the story would be a bit different. I mean, it is kind of different, but let's say just keep it simple. If you have one node, like multiple GPUs, all of them at one node, if you want to decide which type of parallelism would we go with, the rule of thumb is okay, if your model fits on a single GPU and you want to use your multiple GPUs. Okay, let's put it this way. If you have only one GPU and the model fits perfectly inside one GPU, I mean, there's almost nothing to do, right? Just use the GPU. I mean, you cannot do, I mean, at this point your hands are tied, right? I mean, if you have one GPU, if you can fit your model, then just use the GPU. Yeah, I don't know, maybe it's a bit also redundant, but yeah, anyway. But if you have multiple GPUs, okay, then there would be 2 scenarios here. If you have multiple GPUs and one the model fits on one GPU and you want to maximize throughput by using all the GPUs, use the data, so let's make it bold, data parallelism. 2, the model if you have multiple GPUs and the model does not fit on a single GPU, use tensor parallel. tensor parallelism to, yeah, just use tensor parallelism. And then if you have multiple GPUs and I think there's no reason, almost at this point, I think there's no reason that you for example, if you have, okay, so I mean, thinking about it, I feel like I also made the wrong decision, to be honest, here on my here on the graphs that I showed you. Like, the utilization was bad with pipeline parallelism, and this is also one node for GPUs. So the pipeline was really bad, and then I changed to tensor parallelism. But then the thing is, I probably, by doing this, okay, so since this was only 8 billion parameter model, and the GPU, I think it was A40, if I'm not mistaken, so it had, I think, 40 gigabytes of RAM. So the model, each model would fit on one GPU. So I kind of forced the vLLM to use tensor parallelism, but with doing that, I added some intercommunication overheads probably. So there's a chance that if I also try to test it for data parallelism, then the data parallelism utilization would be higher. At least that's what I'm guessing. Because when you're doing tensor parallelism, it basically, as the picture showed, yeah, for example, the picture in the middle, let me also, I think you have to take a screenshot. Yeah, I think I kind of messed up the stuff, like the utilization, because, okay, so how can I edit this? I don't like the namings here. I mean, data parallelism is okay. B would be tensor. Oops. Would be tensor parallelism. And then the last one would be pipeline. Oops. Okay, so I will explain it now. Yeah. Okay, so I think the reason that I say I messed things up was that, so I had one model, like 8 billion parameter, that I could just fit in one GPU. Yeah, but instead I said that I will that I will use tensor parallelism and put every, like, a bit of matrix on each layer on one GPU. So basically, if you imagine this would be like one full layer of the matrix, I kind of broke it into 4, and then every bit of this matrix, I mean, you can think of it like this. Every part was basically living on another GPU, like basically was distributed. And this is tensor parallelism. And by doing that, of course, if you want to do a calculation on one layer, you kind of have to break the break your input, break these matrices multiplication, and then manage it in a way that you can apply it on these broken pieces, and then put everything back together again, because like everything is kind of scattered along 4 GPUs. And then if you want to kind of calculate your multiplication or like your computations, you have to kind of break them, compute them separately on different GPUs, and then put them back together. So I kind of forced vLLM to use this approach, but since every model could fit on one single GPU, I would be better off just using data parallelism. So I think this was also one downside of my mindset at that moment. And I think if I use the data parallelism, basically every of these all of these vectors, for example here, all of these matrices would be basically copied, and then they would be put on different GPUs, and then every calculation would be done on each GPU, and basically the requests would be shared among these, like using the load balancer that I mentioned before. So there would be less overhead compared to the tensor parallelism. So this is one thing that I think I was mistaken at the time, and at least I'm guessing at this point that if I went with data parallel, I would probably get better utilization or like less overhead in general. So this is also one important factor that I want to also add in the end. My mistake when running the inference on 4 GPUs, I should have used data parallel instead of tensor parallel, since the model would perfectly fit on one GPU, and 2, the overhead, this tensor parallelism has overhead of breaking and combining the calculation between 4 GPUs. Okay, so this is also important. I think it's a good thing to remember. Also, okay. Yeah, I will also mention it as well, of course. And also, it's really good that I kind of realize it now, to be honest. By the way, I see a couple of people joined. I just want to say hi directly to them. So if you enjoy watching what you are saying now, please consider subscribing and liking if you enjoyed so far, or like you thought that the content is relevant to you. I would really appreciate the support. I think at the moment we almost kind of got an insight, a little bit some insights of all the parallelism so far, and we almost talked about all of them, I guess. I think maybe not that much about pipeline parallelism, but yeah, I mean, the pipeline is also kind of, you can also see it in the picture. You basically take some layers of the model, and then you put it on different GPUs. So in a sense, if you have a big model, you kind of break it down into multiple GPUs, but then the way that you break it is, of course, different than the other types. Okay. If you ever used vLLM, you probably came across pipeline terms in the documentation. In the vLLM. Okay, the reason you decide for the one. Okay, and then we were writing about the rule of thumb. So if you have only one GPU, and the model fits on your on one GPU, then just use the GPU. Yeah. So you can't really do anything else about it. But if you have multiple GPUs and the model fits on one GPU, and you want to maximize the throughput by using all the GPUs, you use the data parallelism. If the model does not fit on a single GPU, use tensor parallelism. And I think if also the same way that the vLLM documentation said it, if the model is too large for a single node, combine tensor parallelism with pipeline parallelism. So I think probably, so yeah, it's kind of like a hierarchy if you think about it. Like of course the data parallelism is kind of maybe the baseline somehow, and yeah, for example, for a small model, you if you have multiple GPUs, a small model, you can just use the data parallel. And if your model is a bit bigger and you have multiple GPUs, you can just break them among those GPUs with tensor parallel. and if you can't even fit the model in one node, then you have to go pipeline parallel. So I also would remove this one node. If you have one node and multiple GPUs, if the model, I mean, we can just also copy from the documentation. If the model is too large for a single node, combine tensor parallelism and pipeline parallelism. Tensor parallelism with pipeline parallelism. Okay. Okay, let me get an overview of the I think you have to put some spaces here. We do it like this: 1, 2, 3, A and B. How should they? Okay. So there's a rule of thumb, also the introduction, and then I'm thinking to just write about my use case. For example, I wanted to generate 4,000 4,000 data entries. I want to generate 4,000 data entries on a node with, for X, a 40 NVIDIA GPUs. I wanted to maximize the output. Throughput finish to utilize the GPUs to the to the best way possible. Okay, let me put another section here, maybe. Or yeah, I think it's better if I think it would be better to just first explain different types of parallelism, and then I would say my personal experience with these concepts. So here I will explain what I was doing, like what was the idea. Using I think I also wrote down the model name. Using LLaMA blah 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 instruct. It was even 3 billion. I thought it's 8 billion. Would generate private data entries to compare with golden answers from GPT OSS 120B model. I was working on a single node with 400 nanometer GPUs and running LLaMA blah instruct. I wanted to maximize the output throughput to utilize the GPUs as the best way possible. This was an HPC environment. I also add this, that this was on an HPC, on a HPC environment, or on an HPC environment, on an HPC. Yeah, I don't know. Let's ask. Okay, so it's an HPC environment. So good to know. So also have to change the other. As in an okay. To be continued. Okay, so so at the moment I feel like I have the Oops. I have the structure of the blog post. Content, post, Axolotl, fix. Yeah, fix typo. And then git add site content posts. Commit dash m. And I mean, I could also maybe for now what happens if I get through? Add parallelism types, post, just put add new post, parallelism types for LLM. Okay. Content, posts. Git commit. Okay. So. This is the first draft. I mean, it was good. Felt like a brainstorming, just talking about some stuff. Then you also have to keep these somewhere. Maybe I put it. Okay, is there also save this? Okay, so in general I think today was a good good progress. I'm also kind of glad I remembered some of the stuff that I kind of did wrong. I think it was also really good. What is it? Self-reflection. Let me check. I marked the other post as draft, so there's a chance that I don't see it here, but yeah, but in any case, we made some parts of the post and also the structure of the blog. And by the way, since I also mentioned it, it's good to know, I guess. I push my changes to GitHub, and then the GitHub I added this CI/CD. Yeah, this CI/CD, and then on my VPS I automatically pull the latest image every 5 minutes, and so now that I push to GitHub, a build would be triggered. Git -v. Yeah, this build was triggered 2 minutes ago, and in some minutes also probably my VPS would just pull the changes. So this is also good. I just wanted to mention this CI/CD workflow that I set up on the repository. It's also really, really convenient, I would say. Okay, so I think I will put a pause here, leave it as is for this week. During the week I might come back to it and try to adjust things a little bit, but there's I'm aiming for another stream next week. So if you have stayed until now, I highly appreciate your attention. Thank you so much, and I really appreciate further if you would subscribe or hit the like button. And if you have any other questions, just feel free to drop it in the chat either this week or next week. But in any case, have a good day, have a good night. I wish you all the best, and hopefully I see you again next time on the next stream or maybe on the next video. By the way, if you were interested in the topics, I also created another video. This is also about Axolotl and installing stuff on HPC. So in case if you're interested, you can also maybe have a look. And yeah, it talks about a pain point that I basically had. I was trying to install Axolotl, and then it took me almost 5 hours to install it with the pip, conda, and UV, and this like traditional, not traditional, but in these using these approaches. But in the end, I used the containers, the obtainer. So if you're interested to see more, like interested in the topic, you can also have another look there. There's a chance that you also would like it. In any case, thank you so much again. Have a good day, have a good night, and I hopefully see you next time. I will also stay in the chat for a couple of minutes if you have any questions or any comments or anything. All right, take care. Bye bye.
What's up? I'm doing right. second.
I cannot. Cái béo bé bảo đi nè.